All right, so the next application that we're going to learn is in section 7.2, and it's finding volume. And there's a few different methods to finding volume. The first we're going to talk about is the disk method or the disk washer method. First, we'll talk about the disk method. All right, so the disk method says that we take a function, so like in this picture, y equals f of x, and we rotate it around, here we're rotating around the x-axis. So we're going to make a full circle around the x-axis until we develop a 3D shape. And we're going to be able to find the volume of that shape by taking a disk. So when you learned integration, you learned how to take with Riemann sums and using these rectangles, and you basically just took a bunch of rectangles and added them together is really what an integral is. Well, now we're going to take that rectangle and we're going to spin it into where it will become a circle. So I'll try to demonstrate that here with drawing this. Not that I'm the best drawer, but hopefully you get the idea. Okay. And so what we're going to do is we're going to pull that disc out. So just like a CD disc, we're going to pull that disc out and it will have a certain width and measurement that we can then add all together to find the volume. All right, so using the disk method, when we are given the horizontal axis of revolution, which just means that we're going around the x-axis, then we use this formula, which is the volume is equal to pi times the limits of integration a to b, and we call it capital R of x squared dx. Capital R of x is just the function, but there's a reason that we call it capital R, which we'll talk about in just a minute. So when given the horizontal axis of revolution, like rotating around the x-axis, then we use this formula. Okay. If we're given a vertical axis of revolution, which means that we're rotating around the y-axis, so the vertical axis of revolution, which means that we're going to spin around the y-axis like this. Okay. Then we use the same formula, but instead we'll be in functions of functions of y. So we look from c to d of capital R of y squared dy. Okay. So it works the same. Just the difference in using x values or y values. Okay. So let's do an example. And sometimes the graphing or the imagining what it looks like is the hardest part. That's where Desmos will really come into play and can help you draw some really good graphs. If you are comfortable with any kind of three-dimensional graphing, like in MATLAB or Maple, those are really good ways. You don't have to have it, but it can be helpful to imagine. So let's rotate. So what we're going to do is find the volume of y equals negative x plus 4 around the x-axis. Okay, so we're going to look around the x-axis. And so I'm just going to give a rough sketch of what this looks like, because we also need to know our limits of integration. So I have my graph, and let's see, it's got a y-intercept of 4, has a slope of -1, which means that it's going to hit over here at 4. Okay. So again, just trying to get a rough sketch, at least just so I know what it looks like. All right. And so I'm going to rotate this around the x-axis. So I'm going to rotate it this way. And I'm going to take this. And so if I were to rotate that, it would really make like a cone shape. All right. And so my limits of integration then will be from 0 to 4, right? Because I'm looking at the x-axis. So my volume will be equal to pi from 0 to 4 of negative x plus 4 squared with respect to x. Okay. So now I just do all my integration stuff here, so I need to expand this out. And so when I do that, I get x squared minus 8x plus 16. Now doing my integration, I get pi times x cubed divided by 3 minus 4x squared plus 16x from 4 to 0. All right, I plug in my upper limit, subtract my lower limit. Of course, my lower limit's 0. And so my final answer is 64 over 3 pi. So the volume generated by that function, if it were rotated, is 64 over 3 pi. Okay, so this is using the disk method. All right. The disk method always involves the pivot point being around the x or y axis, so you're always just rotating around a line that the function is connected to, if that makes sense. So here, this negative x plus 4 is connected to this y, or around the x-axis. Okay. What we want to talk about now, though, is if we want to find maybe the volume generated by a section that's rotated that's not connected. So as an example here, you see this f of x and g of x create this area, this region, and if we rotated that region around the entire curve, we wouldn't generate a full circle, or a solid shape rather. There would be this solid shape with this center cut out, because that is the gap between the bottom function and x. Hence, this is the washer method. So if you think about like a washer, like the hardware, it's just that circle. It's got a width, but the center is hollow or has nothing there. Now we would be pulling washers out. So it's just an offshoot of the disk method, but it's called the washer method. And the washer method works similar to the disk method. So what we have is that the volume is equal to pi times your limits of integration of capital R of x squared minus lowercase r of x squared dx. Okay, so just to show you, capital R is like the disk method, right? That full function. But then we're going to subtract off the lowercase r of x, which is just the gap, or the difference between the bottom of the region and the axis. Okay. So let's do an example, and let's find the volume around, so we're going to rotate our function around y is equal to 4. Okay. And we're going to use the region y equals x, y equals 3, and x equals 0. So we are going to use that region and then find the volume that region creates. So first we need to develop a graph to show our region. Again, this is where Desmos really comes in. If you want to use that as a graphing tool, graph it by hand is fine. If you're comfortable with using any other kind of graphing, Maple, even TI calculator, so on. Okay. So I'm going to just write my graph here. And it doesn't have to be perfect. All you need is a rough sketch. All right, so I have x equals 0, which is just the vertical axis, y-axis. So I'm just going to kind of color that in. Okay. Well, all right. And then I have y equals 3, which is up here. So there's 3. I have y equals x, which is just a line. So here's y equals x. So what I'm going to do is take this function and I'm going to rotate it around y equals 4. Well, y equals 4 is up here. All right. So what I have to develop is my capital R of x and my lowercase r of x. My capital R of x, again, represents the region from the axis of revolution to the bottom or the top of the function. Well, my function is really x here. So what I have is my capital R of x will be my top curve, so to speak, which is 4, minus my bottom curve, which is x. So my capital R of x is 4 minus x. This is the thought process that goes into developing R of x, or capital R of x and lowercase r of x. Okay? Little r of x is represented by the gap between my function and my axis of revolution, which here is just from y equals 3 to y equals 4, which is just 1, because it's just a gap of 1 between my 4 and 3. Now I can just use my formula here, just plug everything in, but we also need our limits, but I'm going to plug in r of x, so I have 4 minus x squared minus 1 squared, all with respect to x. All right. But my limits are just those intersection points. Well, they intersect when at 0, and they intersect at 3, right? Because y equals x, so therefore it equals 3 when x equals 3. So my limits are from 0 to 3. Okay. So then I expand it out and I do my integration part, and I get that I get x cubed over 3 minus 4x squared plus 15x from 3 to 0. I plug in my limits of integration, 3, subtract off the integration with 0, but of course that's just 0. So I plug that in and I get 18 pi. So if I were to rotate that around and create an open washer, the volume of all those washers added together, or that region, is 18 pi. Okay? So again, the key points here for this are developing your R of x and your lowercase r of x. The integration part won't be a complicated process because it's all just basic integration techniques. But it's just an application of integration. And we'll get into some more applications of integrations later in the chapter. But if you have any questions, please feel free to email me. And as always, have a great rest of your day.